All right. So, does everybody understand this? Okay.
The plane.
Saying that. They did that. There you go. Tell your neighbor. Correct answer is B. Okay. Just like in the plane, the ultralight, it floated because it looked like it, but it was falling, just in the contact and confines of the ultralight. Okay. So, have you ever heard the story or something about Isaac Newton sitting under an apple tree and being hit with an apple, and like that was supposed to be some significant thing in science, something with gravity. Like, okay, here's how the story goes. Isaac Newton is trying to figure out how the moon does what it does. Like, yeah, don't know. Like, why does it stay there? Like, what keep? Like, I don't. And so he's sitting underneath an apple tree, pondering this one day, looking up at the moon. Like sometimes you can see it during the daytime, and an apple happens to fall out of the tree, hits him on the head, and he's like, "That's it. The moon is like an apple. They're both falling. That's it." And people are like, dude, there's a fine line between genius and insanity. We're pretty sure you just stepped over that one. And he was like, no, 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 check this out. So he came up with this analogy to try to explain what his realization was. So let's say we have a platform with a cannon on it, okay? And we shoot the cannon horizontally, and then we shoot it faster horizontally. Which one's going to hit the ground first, A or B? Same time, okay? Well, what happens if we dig a pit? Which one hits the ground first? A does. Good with that? All right, so then what he said was, well, instead of building a platform, let's build this ginormous mountain that goes above the atmosphere, okay? Like a million times bigger than Everest, okay? Imaginary. And we have an equally imaginary big cannon on top of this mountain, okay? And we shoot the cannon, falling, falling, and then we put more gunpowder in it, and we shoot it faster, falling, falling, falling. Which one's going to hit the Earth first? A or B? A, because of the curvature of the Earth. Does that make sense? So let's put some more gunpowder in it. Falling, falling, falling. Put more gunpowder in it. Falling, 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 falling. More gunpowder. Falling, 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 falling. More gunpowder. Falling, 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 falling. More gunpowder. falling, 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 duck, falling, 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 falling. What do we just do to this cannonball? We put it into orbit. It was always falling. It just never hit the ground because it was going fast enough and never hitting the earth because the earth was curved, and it just keeps on falling. And he's like, check it out. The moon is like an apple. It's always falling. It's just moving fast enough that it never hits the earth. And people are like, oh, you are a genius. Okay, does that make sense? So theoretically, if you threw or launched an apple fast enough, you could put it in orbit. Problem is that'll never happen like within our atmosphere because it'll burn up just like meteorites when they go through, like shooting stars. They burn up because they go through their atmosphere. If you shot an apple as fast as it needed to go in orbit, it would just burn up like. Okay? Gonna do it. Make it happen. Okay? Do what? Yeah. Okay? All right. Talk to your neighbor. C for creeper. Okay. All right. Correct answer is C for creeper. Yeah. There you go. Prior to yesterday's lesson and today's lesson, I would venture to say that a lot of you would have said this. Okay? Is there gravity above our atmosphere? What's holding the moon? The Earth's gravity. Okay? Does that make sense? There's still gravity. They're just always falling. Is everybody good with the drop zone? Okay. So, what would it feel like to be an astronaut? Just like that. That's what it feels like to go to outer space. You just get used to it after a while. Crazy. Okay. All right. So, um, astronauts that go in the space station have to do regular workouts because their muscles aren't being exercised because they don't have to lift anything or even themselves. Like they become atrophied. Kind of like the same thing when you take off a cast after a while, like your muscles are really weak. You need to do workouts and stuff. So to have sustained life in space, one of like sci-fi movies have space stations that look like donuts that spin. Okay, the idea is it works like the barrel of fun ride, or like the whirly tilt-a-whirl, or like, I don't know, gravitron, or I don't know what they call it, the ride where you get pinned up against the wall. Okay, but if it spins too fast, you're gonna get people throwing up. But you got to get it just right so it's spinning enough so that the normal force is equal to their weight, and so it feels like they're in this place where there is gravity, but there really isn't. Does that make sense? Okay, so there you go. Now, the rest of the class, sit back and enjoy the show. If this is more like Earth space science, if the sun was a basketball, how big would the Earth be? Okay, would it be the size of a tennis ball? Size of a golf ball? Size of a marble? Size of a pea? Size of a pencil eraser? Size of pencil lead? Okay, if you get out your pencil and look at the diameter of the lead, cross-sectional area, specifically if you have 0.7 millimeter lead, that is the size of the Earth. You're on there. Little video, like and everybody else. Okay. Now, if the sun was a basketball, where would that pencil lead Earth be in relation to it? Would it be here? 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 Would it be half the classroom distance? Would it be the whole classroom distance? Would it be edge of the hallway, like the corner of the hallway? Pencil lead would be at the corner of the hallway. Pencil lead from the basketball. Pluto. I know it's not a planet. Pluto would be a half a mile away. It would be at the fire station up here or the stoplight at 500. Chipotle is too far. Yeah, you're out of the solar system. The nearest star to the sun, if the sun was a basketball, would it be the courthouse? Would it be Indianapolis? Where's the nearest star to the sun if the sun was a basketball? How close in this scale model, how close is the nearest star? Would it be the courthouse? Would it be Indianapolis? Would it be St. Louis? Would it be Atlanta? Hawaii. The nearest star The nearest star to the sun, if if our sun was the size of a basketball, would be Hawaii. Okay, that's the closest star. The closest. Okay, so do you see how? So it's like, hey, there's us. Whoa. Okay, that blue ball right there is Neptune. That's not Earth. That's our sun right there. Right there, that's our sun. That's our sun. You can still see our sun. Still see it. Our sun's gone. You can't see our. That is not our sun. That's the really big one. Oh, wait a minute. There's bigger. Ah, we'd be dead. That would engulf like Saturn. Oh, well, just that color. Okay, lights coming on. All right. So space is big. Miles just don't do it. So we need another type of measuring for distance. Okay. So how fast does light go? It goes fast enough to circumnavigate the Earth 7 times in 1 second. And one Mississippi, 7 times around the Earth. Okay, that's pretty fast, like really fast. Okay, it takes light 8 minutes to go from the sun to Earth. Okay, to go from our basketball to the edge of the hallway. Okay, now the nearest star, it takes light 4.3 years to reach Earth. You good with that? Now, um, what we say, the unit that we're going to use for space is light years. What that is the distance that light will travel in 1 year's time. Does that make sense? How far light travels in 1 year time. So it takes 4.3 years for light to travel this distance. So Alpha Centauri is 4.3 light years away. It's not a unit of time, it is a unit of distance. Okay? The sun is 8 light minutes away. the Earth's circumference is 1/7 of a light second. Okay, does that make sense? Are we seeing how we use that as a distance thing? Okay. Now, so our galaxy is over 100,000 light years across. If you could travel the speed of light, you could not get across our galaxy, just our galaxy, our Milky Way galaxy, in 100,000 years. Okay. Now, looking at Earth, space is big. Okay. But looking at Earth, astronomers have called Earth the Goldilocks planet. It's not too hot, not too cold. It's just right for life. Okay. And here are some of the major characteristics of Earth that make it special. Okay. First off is the mass of the planet. The bigger the mass, the stronger the pull of gravity, the force of gravity, the gravitational field it has. Okay. The gravitational field, the pull of gravity, is what is responsible for trapping gas molecules to itself to create an atmosphere. Okay, that is why we have an atmosphere, is because of gravity. It pulls the gas molecules into the planet. Okay, if the planet is too big, the gravitational pull is too strong, and it traps a whole bunch too much gas and creates really thick atmospheres. And that's what this is what we have for the giant gas planets. Okay, Jupiter, Saturn, Neptune, and Uranus. Okay, they're huge. But their core is way down deep in them. Sunlight doesn't get there. That's kind of a necessary ingredient. Okay? But if it's too small, then the gravitational pull isn't strong enough to keep that atmosphere in there, and that's why Moon doesn't have an atmosphere. Mars has a very thin atmosphere. Mercury, good luck, like not even. Okay, so Earth is just right. Another characteristic that Earth has that makes it special is it has a molten core. It has, and we'll talk about this later when we talk about magnetism, but the convection currents inside the core of the Earth create this magnetic field that protect us from solar winds. So you have high radiation cause a lot of cancer. If we didn't have that, life would not do well. It would also, the solar winds would also rip off our atmosphere. So this protects us, this magnetosphere. Okay, so we're looking for a planet that has this molten core. Ben, it does not. Now, it might have at one point, but I don't think it has it. Okay. So not only are we the right size to trap an atmosphere, but the ingredients that make up our atmosphere are great. Okay. We have this, and these are rough estimates, 75% nitrogen, 20% oxygen. Okay. What this enables us to do is that combination protects us from ultraviolet rays that would cause cancer. Okay. Like the ozone layer, like we need to protect that, like that protects us from infrared rays or ultraviolet rays. That's a thing, like it's a good thing to have. Okay. The thickness and the ingredients also provide a good climate and allows for liquid water. Why is liquid water good? So I actually didn't know this until like 2 years ago when I was researching this. Water is actually the second most abundant compound in our universe. Uh, Hydrogen gas is the first, but most times where water is found is in ice. Like it's ice. It's not liquid. It's frozen. Um, Water wise, why do we need liquid H2O? Because it's a good solvent. It dissolves molecules. It can combine stuff. It transports nutrients. It absorbs a large amount of heat. In chemistry, you learned about water having a high specific heat capacity. It can absorb a lot of heat and not change its temperature very much. So that helps keep the climate good. Um, and a characteristic of water is that when it freezes, it expands, which is not normal. When things get colder, they contract. The benefit to that is if it contract, if when it froze and ice contracted, it would sink, and lakes would freeze from the bottom up, and all fish would be like, what? Okay? So another aspect of the Earth that is unique, that is special, is that it has plate tectonics. Okay, and what plate tectonics help regulate is the carbon cycle, the carbon dioxide, how much carbon dioxide we have in our atmosphere. Okay, um, so if carbon dioxide levels become too high, you get this greenhouse effect, and it warms up the Earth. Like average temperatures get hotter. Okay, um, Venus has a bunch, it's the right size, but it has a lot of CO2 and no life is on there because it just cooks it. The temperature of Venus is too hot to sustain life. Um, and so CO2 is recaptured out of the atmosphere when living things die, like plant life, animal life, die and then become sedimentary rocks, and that becomes part of the plate tectonics. And over time, um, if the CO2 levels become too cold, then you can get an ice age, which has happened. Um, but the plate tectonics warm things up because as this goes under, volcanoes shoot out large amounts of carbon dioxide into the atmosphere, creating a greenhouse effect and warming up the earth and ending the ice ages. Okay, so there's this cycle of carbon dioxide, and a lot of things contribute to it. It's not just a one type of thing. You got volcanoes. We just talked about that, but you also have a bunch of life in the ocean doing its carbon cycle stuff, dying, uh, eating, breathing. Life on the earth does its thing. And then you got us doing our thing. Um, so it's a big cycle. There's not just a one factor thing. Okay. We hear a lot about carbon dioxide levels in our atmosphere. Okay. That's been a really popular thing the past 20, 30 years. Okay. Linked to global warming. Okay. Um, Here's a very general piece of advice. How do I preface this? When things, when you have things that are trying to influence people, you gotta be skeptical. You gotta question. You gotta like, what's the motive here? What are we talking about? Why would people want to say what they say? Is it to reveal truth, or is there something that is is there something going on? Another kind of underlying question, a more specific question under that topic is like, who's paying them? Like, where's the funding coming from? Who's like all that stuff. So let me just specifically talk about global warming. Okay, hot topic. Heard a lot about it. Okay, here's the data. Okay, since 1880, the amount of CO2 emissions have increased dramatically. And we've measured the Earth's temperature matching that. It's valid. It is very true. Okay. This is a better chart. Okay. Because that just took it from 1880. Here, this looks at thousands of years. So we're at hundreds of thousands of years. Okay. I've seen this chart a lot too. Okay. Here we got ebbs and flows, cycles in CO2 emissions, or just CO2 measured in our atmosphere. And we can measure that in the rock layers. Okay. And here's this line here. This is like, hey, we're right here at 1950. That's the beginning of the Industrial Revolution. And look at that. Like, there's definitely a spike in how much CO2 is in our atmosphere. Okay. But that's 800,000 years. If we zoom out to millions of years, like, just kidding, billion of years, 4.6 billion years. This graph here just shows us that. The purple is the CO2 content in our atmosphere over the last millions of years, hundreds of millions of years. Folks, we're at an all-time low, like other than this point here. There's been crazy amounts of CO2 emissions in our atmosphere over the millions of years. We're at an all-time low. It's going to go up. There's nothing you can do about it. Like we're at the low part of the cycle. It's going to get more. Okay? Temperatures on Earth are going to get warmer. That's what the blue line represents. Okay? It's just the cycle of life. Like, it's just, now, am I suggesting that you go out and get your big trucks like let's burn it? Like, no, that's not what I'm suggesting. Like, be responsible. Be responsible with what our planet is a special place. Does that make sense? Like, do, but recognize, folks, we're at a low. We're gonna, like, the cycle means we're gonna go up. Does that make sense? Like, how much factor? Now, do we have an influence on that? Can we slow that down at all? Yeah, maybe. But like, it's going up. Polar bears are gonna die. Nope, kidding. Polar ice caps will melt. That's just, but okay. So all I'm saying is, folks, when you look at data, be skeptical. This first chart is valid. They're accurately describing that. They just did it in a very small thing to paint a picture. You gotta look at big pictures. You see how I'm getting, like, where I'm getting at. Gotta be skeptical when someone's toting like, "Hey, this is how it is." Like, okay, well, okay. Another thing that makes the Earth a special place is the moon, the size of the moon. Um, it is the perfect size to maintain and a certain distance away to uh, cause tides, but also our axis is tilted. And like the moon enables us to keep that tilt stable. Okay. Why is the tilt important? So it would grieve me greatly for you to like walk out of high school and not know why the seasons happen. Here's the popular answer. Here's the sun. Here's the Earth's orbit. Summer when it's closer, winter when it's farther. Okay? If that model was true, everybody on Earth would experience winter at the same time, and everybody on Earth would experience summer at the same time. Does that make sense? But that's not the case. The northern and southern hemispheres are flipped, like they have opposite seasons. It's because of the tilt of the Earth. And here's why the tilt of the Earth causes seasons. When you go to the beach, where do you put sunblock on the most? Like, where is it? Like, what parts of the body? Like, oh man, I better get sunblock on that. I'm going to get burnt. If you're not sunbathing, you're just playing. Tops of ears, noses, cheeks, shoulders, tops of feet. Okay. It's me, top of the head. Okay. It's anywhere where the sunlight comes directly on, like perpendicular to your body. That's what's going to get burnt the most. It's not that my shoulders are closer to the sun than my feet are. That has nothing to do with it. It's not a distance thing. It's an angle thing. Oh yeah. Actually, it's not that bad. I mean, I haven't gotten like totally fried, but it's surprisingly, I was like, oh, it doesn't hurt that bad. Um, so, okay, let's say the sun's over here. Okay, sunlight is coming in this way. Okay, in this, at this arrangement, the southern hemisphere is experiencing summertime because the rays of light are hitting this perpendicular more directly. The northern hemisphere, it's not as direct. So the northern hemisphere gets winter, and the southern hemisphere gets summer. But if the Earth is on this side and the tilt is still like this, then northern hemisphere is getting summer and southern gets winter. It's not a distance thing. It's an angle thing. Does that make sense? Okay. And we need the sun to prevent like the climate. Sorry, the seasons are great because it gives a chance for things to thaw out. It gives the things to cool down. Like it's a cycle that keeps life going. Like a lot of things die if we have a long winter. Um, the moon allows us, so we've only shifted, our tilt has only shifted by 1.5 degrees over a million years. Versus in Mars doesn't have a moon. It's shifted, its tilt axis is shifted by 50 degrees over 100,000 years. Like crazy wobbly. Like that is not a sustainable climate that like maintains life. Okay. Now, people have argued, well, you know, well, no, we won't get there yet. All right. So, life as we know it is carbon based, meaning that carbon is the foundation of molecules that build life. Okay. Carbon, if you remember from chemistry, has 4 valence electrons. So there's lots of opportunities for things to bond to it. Okay. And it is in organic chemistry, carbon is the foundation that allows for crazy molecules with hydrogen, nitrogen, and oxygen. Um, so the theory is like, well, does it have to be, does life have to be what we know it to be? Could it be like some other uh, element to be the foundation? And so they're like, well, maybe silicon could be the foundation, or boron. They have some properties like it, and they've tried in the labs to create living molecules, or not even living molecules, just molecules that could be complex enough to sustain, to like do something like that. And it hasn't been done yet. Okay, so at the moment, like carbon based is all we know that can exist. Okay, so you need all these parameters for life. Okay, um, we'll stop there. That's as far as we got with all the other classes. So remember, you have a worksheet due tomorrow.